development of a humanoid robot. And the key takeaway from my presentation, hopefully I try to finish my keynote speech within 1 hour. The key takeaway include 2 truths. So these 2 truths actually is quite obvious to many people, but however, to our research community, we still believe that the brain include mind is a part of the brain. So I believe we must consider like human being as an embodiment of a biological body, biological brain, and the intelligent mind. And inside the mind, we have at least 3 types of mind there, all right? And the second truth is about the common ground between biological brain and the electronic computer. And a lot of people believe that the human brain is a massive network of a neuron. Actually, this kind of understanding does not help us to advance the research. It is equivalent to say that the robot is a massive network of a molecule. But this kind of a statement is true, but does not help us to understand the nature of a robot, all right? So actually, the common ground should be logical gate and the devices, not the transistor or neuron, all right? Then the key takeaway also includes 3 know-how, all right? The first know-how is about design of the humanoid robot's body. Second know-how about the electronic brain, and the third know-how, that is the most difficult part, which is about the intelligent mind, all right? Then in order to help you or help us to understand how to translate these 3 know-how into solution for the achievement of the design of humanoid robot, I try to group all the related topics into these 5 layers of a flow: material flow, energy flow, signal flow, motion flow, and then lastly, knowledge flow, right? So I can skip the introduction about myself. So let's start with today's keynote speech. So basically, I will follow this guideline, and today's talk include 2 parts. One is philosophical, and the second part will be more technical, all right? So in the philosophical part, I will try to answer these 2 questions: why to focus on humanoid robotics research, and what are the know-how behind the invention of a humanoid robot. And the second part will be more technical, all right? So I will zoom into the detail about these 5 layers of flow, okay? So let's start with the answer to this question: why to focus on humanoid robotics research, okay? So one way to answer this question is quite straightforward. If we look at our mission on Earth, basically we know, okay, we have 2 major missions. Number 1 is to understand the world. Number 2 is to improve the world. Then how to understand the world, how to improve the world, and obviously research come first, all right? Therefore, we want to know what is objective of research, what should be the driving force behind the research, what should be the outcome of the research, right? So here, I believe research has only single objective, which is to create value, all right, by finding better way of solving the problem, all right? And there are 2 driving forces behind research. One comes from scientific problem, and the second one comes from social need, right? And there are 3 possible outcomes from our research. One is to create better theory, another is to create better technology, and then lastly, we must create a better product, right? Then it is interesting to know, okay, how to understand the universe. And you see, the advice from Nikola Tesla is to think in terms of energy, frequency, and vibration. And for AI research, or for the design of a robot mind, I guess it is better to think in terms of a space, vector, and the time. And later on, I will illustrate this statement with a slide, all right? And also, if we want to improve our world, we need to have a big view about the whole universe. At the top 3 layers, we must think in terms of a system, device, and the material, okay? Then, okay, how to improve the world? the answer is quite obvious. We need to invent a smarter products, smarter machines, smarter system. And among all the best inventions are made by human being, I believe a humanoid robot should be the most advanced one, right? And there are three motivations for us to focus on humanoid robotics research. Number one, humanoid robot is the best platform for us to develop human-like skill and human-like intelligence, all right? And some people may talk about the 5C, and here you can identify these 5C. 5C refer to computing, communication, control, cognition, and cooperation, all right? Today, the weak pillar should be cognition, all right? Also, people talk a lot about the cooperation, but without the cognition capability, it is very difficult for us to cooperate with robot or machine, etc. Right? And the second motivation is because humanoid robots are the best platform for prototyping. Because you see inside the humanoid robot, we have a module for manipulation, module for grasping, module for leg locomotion, and also vision system, speech system, etc. Right? So this is the best platform for us to do prototyping. Right? The third reason is humanoid robots are best platform for education. And you know, okay, today it's very difficult to teach STEM, STEM in school. Therefore, we can develop a robot tutor, okay, let robot to play with the student, then in this way, okay, to cultivate the interest of a student to do learning of let's say science, technology, and engineering, mathematics, etc. Right? So these are the three motivations. The next question you may ask is about the readiness for us to venture into humanoid robotics research. The answer is yes. Actually, we are ready to venture into humanoid robotics research. And in particular, I believe humanoid robotics research will drive AI research. And later on, I will highlight a little bit. You see, the AI research have a special history, etc. Right? And since we have three strong foundations, right, which are ready for us to leverage on in order to venture into humanoid robotic research. And these three foundations are robotics, computer science, and artificial intelligence, all right? So I just quickly go through the history of robotics, history of electronic computer, and the history of artificial intelligence. And in this way, you understand, okay, we have a three strong foundation for us to venture into humanoid robotics research, okay? But if you look at the history of robotics, it is quite interesting to discover that the first robot actually was invented in China. If we agree that the teleoperated robot are part of a robot family, right? The puppet or shadow puppet actually is the first generation of a teleoperated robot. Okay, so I skipped the video. So I have recorded a keynote speech placed in YouTube, and the live will last more than 2 hours, right? So here I'm not going to play the video, otherwise I may not have enough time to go through the key point. And obviously the key contribution in the history of robotics come from a Western country, all right? So the terminology of a robot, terminology of a robotics, the 3 rules in robotics, all these are the contribution from a Western country, all right? And the first industrial robot and the first company which commercialize robot product all come from Western country, etc. But however, in Asia, Japan is a special country which continues the tradition in China, and with government support and a single country in Japan, then you see they have made a tremendous progress in the development of a different type of prototype of a robot. And if you want to look at the top 4 industrial robot company, actually 2 of them come from Japan, right? Like in terms of a humanoid robot research, like you see the Honda's prototype is among the best one in the world, right? And then we want to know, okay, who are the major players of a humanoid robot around the world, right? So in Europe, we can name these countries like France, Italy, United Kingdom, and Germany, all right? And recently, I guess America, okay, attract a lot of attention from the media, etc., right? So then the top player in Asia obviously come from Japan, South Korea, and also China is a catch up, right? And in the USA, United States, and the leader should be Boston Dynamics, and Elon Musk also want to venture into humanoid robotics commercialization. And okay, so this is quite interesting for us to see. Okay, this become a very, very hot topics. Okay, and in addition, DARPA actually has launched a robot challenge, but that robot challenge actually is a humanoid robot challenge. Okay, so that challenge was launched in year 2015, and you will see the scenario basically is for humanoid robot to achieve a certain task in the human environment or made for human environment. Okay, so from here then you see, okay, humanoid robot eventually could serve as a robot worker, robot helper, robot driver, robot tutor, right? So it could play a lot of role, right? Then, okay, then we want to know, okay, in terms of a skill, if let's say you look at the skill demonstrated by ASIMO, skill demonstrated by Boston Dynamics humanoid robot Atlas, okay, there's not much difference between human skill and the robot skill. Then how's about the human-like intelligence, right, or human-like brain? So actually, there is a big gap there, right? So then the good news is in parallel, okay, to the robotics history, there is a computer science history, all right? And there's a very, very important person in the development of electronic computer. Also, before electronic computer, there are some invention about the mechanical computer. But today's major contribution, I guess, come from John von Neumann, okay? And also he has written a book about the similarity between human brain and the machine computer. But unfortunately, he has passed away before he could finish his book, etc. And there are many other people try to write a similar book about the similarity between brain and the computer. But this is a very, very interesting topic to think about the similarity between human brain and the electronic computer, right? So now let's look at the history of the electronic computer. And then you will see actually the first generation of electronic computer was invented or developed in year 1945 in Pennsylvania University, but this is a military project, all right? Then subsequently, we have gone through 4 generations of electronic computer at least. So you have generation 1, which make use of a vacuum tube, generation 2, which make use of a transistor, then generation 3, which make use of an integrated circuit, then generation 4, which make use of a very large scale integrated circuit, etc. Then we may ask this question, what will be the next generation of electronic computer? So it is interesting to know, like if you search the internet, Japanese company has launched this 5th generation of a computer, I guess 20 years ago, but that is a failure because I believe they do not know exactly which direction to go with the project of a 5th generation of computer. So today, I guess it should be quite clear, okay? The next generation of a computer should be human brain like the computer. Therefore, it's interesting for us to know what is a human brain, okay? What is the common ground between human brain and the electronic computer, right? And then here, this is my, okay, believe that the humanoid robot research will drive, okay, the history of electronic computer to move toward the direction of human brain-like computer, right? So Okay, that's about the second foundation for humanoid robotics research. Then how's about the third foundation of humanoid robotics research? The third foundation should be AI, but actually behind it should be the man. I believe intelligence arises from man, but not arise from the brain. But however, if you look at the history of AI, you will see the history of AI started with the study of artificial neuron, because a lot of people believe that the human brain is a massive network of a neuron. All right. If you use that term, it is equivalent to say that a robot is a massive network of a molecule. All right. If you just look at the molecular level, it does not help us to understand. So we must move up level, right? But later on I will mention. Okay. So this is why then we have a two wave. Okay, up and down, up and down. Then here you see there are two AI winter, right? And also you see the Turing test, right? So obviously this initiate a research into the direction to come out the objective criteria to judge the intelligence level of future machine. But Turing test itself, I believe, is not so scientific. All right. Okay. So then how come AI has such a special history? I believe one very influential book, it was written by Francis Crick. He is a Nobel Prize winner for the discovery of DNA. And he made a suggestion in his book. He says by analyzing the signal inside the neuron system in our brain, one day, eventually we may discover what is a human mind or what is intelligence, etc. And this idea actually has a great influence to computer vision research. You know, in MIT, there's an AI lab, all right? And there's a group of people doing research in computer vision. So more or less, they follow again this suggestion, okay? So, but from engineering point of view, I do not believe that by analyzing the signal emitted from the motherboard or microprocessor, you should be able to discover the blueprint of operating system. I guess it is not likely, right? And then, since many people believe that the intelligence arises from brain and the mind is part of the brain, so this is why you look at the whole world. Okay, so a lot of brain initiative, very little mind initiative. Also inside the brain initiative, we include, okay, the little bit of research about the AI. Okay, so for example, in US, we have a brain initiative. In Europe, in the same year, we also have a brain initiative with a huge investment. And 1 year later in China, also has a AI initiative, a robotics initiative, etc. Right? And then, okay, here is a big question. Why do we believe that the intelligence, is not arise from the brain, and in particular, the biological development brain has nothing to do with the design of the mind, all right? And for those of you, if you pay attention to manufacturing, actually there are three types of manufacturing: mechanical manufacturing, chemical manufacturing, biological manufacturing, all right? So manufacturing is a process which has no direct link with the design of the mind or design of the brain, all right? But this is why people just confuse with biological manufacturing. And in particular, if you pay attention to the nature of biological manufacturing, you will understand the nature of evolution, all right? So people say we are the result of evolution from a fish, from the monkey, then human being. Actually should be reversed. Monkey is actually maybe is a diversified version of a human being, if you think carefully about the biological manufacturing. So this is another topic. So it's very interesting to pay attention to manufacturing, so you will have a clear idea about a lot of misconception in AI and also in the theory of evolution. Okay, and here I have actually I have a full video to support this conclusion. Okay, why intelligence arises from the mind. Okay, but due to the time constraint, I skip this one, because you can watch the recorded keynote speech. Okay, and you see today a lot of research, a lot of investment, okay, into the learning, deep learning, etc. And in year 2003, I already set this condition, okay, for anything to have a capability to learn, okay, then you must reach this level of being educable, right? I guess is at the end of my book. And also 1 year later, you see the Bill Gates statement, if we make any breakthrough in artificial intelligence and machine learning, all right, then the result will was 10 Microsoft. And today, we do not see the breakthrough, right? Okay, so then what's wrong with AI research in the past 17 years, all right? So here I give a comparison, all right? So one is because we believe mind is what the brain does, all right? Then actually the truth should be mind is mind, brain is brain, okay? And then in the old paradigm, there is a belief that the mind comes from evolution. That is wrong, okay? Evolution because it corresponds to biological manufacturing. Manufacturing has no direct relationship with the design of a product itself, all right? So it's quite clear. So mind comes from design. That should be the correct conclusion, all right? Development without the design. So that is true because development corresponds to manufacturing, and the production always comes after design. You product design first, and then you do manufacturing or production, etc. And today, a lot of achievement could be categorized into this title, computer-aided human intelligence. However, public expectation should be machines self-intelligence, all right? And for those of you doing the deep learning, I believe inside the deep learning, a lot of activity should be labeled as a tuning of this network system, all right? But tuning has nothing to do with the learning, all right? So then a lot of people believe that the learning is key to AI. I believe design is a key to AI, okay? So then we can make a new definition of AI. So if you look at the achievement in the past 70 years in the AI research, all right? And I guess the majority of them could be classified under these topics of computer-aided human intelligence, all right? But these results are useful, but it should not be the core focus, okay, of AI. AI basically should be studied with the objective of achieving machines self-intelligence, etc. Then what should be the key issue behind achieving machine self-intelligence? Then here I just highlight, okay, basically it's a transformation from a signal to cognitive state of knowing the meaning inside the signal. That should be the focus, all right? Then you may ask this question, are we able to achieve this transformation from a signal to knowledge, knowledge to knowledge, and knowledge back to the signal or motor signal? Okay, first transformation is from a sensory signal to knowledge, knowledge to knowledge, then knowledge back to motor signal. So actually, we have some preliminary result, for example, XI coordination, all right? So we have a constant matrix to transform the knowledge or visual signal seen by binocular vision, then back to the signal, okay, for the motor to perform. So this is actually this closed loop already. Okay, transformation from a sensory signal to knowledge, knowledge to knowledge, then knowledge back to motor signal, right? That should be the key focus of AI research, right? Okay, then and here we do a simulation, and this result has been actually is broadcast in the national TV in Singapore because we validate this result with a robotic arm at that time, all right? And this result has been shown in the national TV. Okay, so I move on. And 10 years later, in Pittsburgh University in USA, they do a study, validate actually the result with a monkey, right? So use monkey's eye, monkey's brain, get the signal, then control the robotic arm. Then you see that the loop has been closed, etc. Right? So it's also quite interesting. And then subsequently, we move on to do hand-eye coordination. Actually, hand-eye coordination is a typical example of this outer loop of intelligence, because this outer loop includes a transformation from signal to knowledge, knowledge to knowledge, and then knowledge back to signal, etc. right? So then for lagging the locomotion, and this also video has demonstrated to the Ministry of Defense in Singapore, right? Because this project was supported by the government, etc. Okay, so that gives you I guess strong answer about the motivation for us to venture into humanoid robotics research, because we have a 3 motivation, we have a 3 foundation. All right. So then next question you may want to know, okay, do we have enough know-how so far for us to venture into this direction? Then what should be this know-how? All right. So then, okay, the good news to you is we must have, we have a 3 know-how. All right. And in order to develop a humanoid robot, okay, we need to know what is a humanoid robot, right? And in order to know the answer to this question, what is a humanoid robot, we need to know what is a human being. Okay, now you see in the research community, there are 2 versions of the answer. Most of us believe that the human being is the embodiment of the body and the brain. That's it, all right? But that is too simplistic answer. So we must clearly spell that the human being is an embodiment of the body, brain, and the mind. Brain is brain, mind is mind. In particular, for those of you, you can do a little bit research to find out the textbook written by people in religion more than 2,500 years ago. Okay, I guess 2,500 years ago, there's no science journal, right? But it's very interesting. Okay, the textbook in that period of time already tell us what is a mind, what is intelligence, and also what is life, right? Because more than 10 years ago, I'm also interested in this question of what is life, okay? I do not know the answer. And suddenly I discover actually in religion, okay, they know the answer. So their discovery is very simple. There are 3 types of a mind. We have a coarse mind, subtle mind, and the deep mind. Subtle mind, deep mind actually form a life. Life never die, okay? So it will continue. And that explains the process of reincarnation, right? And by default, when we talk about the mind, so it refers to the coarse mind, right? So it's very simple. And but today we have a YouTube. There are a lot of evidence that you can find in the YouTube. But the problem is people in religion, they do not know today's terminology in science. This is why they are not able to explain, okay, to the public with today's terminology or today's language, right? So this is just for you to know, okay? Then with all this knowledge, okay, if you consolidate all this finding in science and in religion, it's very clear to us, okay? Today the definition of robot should be like this, okay? A robot is an embodiment of a body, brain, and the mind, which could undertake, okay, execution of motion, performance of a task, and the most importantly is interaction with the people, and in particular interact with the people at the cognitive level, but not just at the signal level, right? Then, okay, if we agree with this definition, then what should be the know-how for us to achieve the invention of this type of a robot or machine, all right? So know-how number 1 should be the design of a robot's body, but today there's no issue at all, okay? So with today's advance in robotics, okay, so we have all kinds of actuator, sensor, controller, etc. All right. Then the second know-how is how to design robot's brain. Okay, but here is interesting, the design of brain, which is a massive network of neurons for the purpose of creating numerous CPU and a huge memory. But here you see, should we just stop at this statement, network of a neuron? But the good news is with the neuron, we are able to come up with the solution of for the logic device such as AND gate, OR gate, and the XOR gate, etc. Here I just show you some example. Then with this logic device, actually, then you will see, okay, what is today's electronic computer? You must say today's electronic computer should be a massive network of logic gate and the device, but not transistor. If you just say today's computer is a massive network of transistor, it does not make too much sense, all right? So interestingly, if we move 1 level up, then we unify the human brain and the electronic brain. Okay, so both of them actually could have this common ground of a logic gate and the logic device, right? Then with the logic gate, logic device in computer engineering, it is a common knowledge that we are able to come out a solution for memory, come out a solution for ALU, right? Then in this sense, we must think about what is the true nature of a human brain. So actually a human brain should be a massive network of a logic gate and the device for the purpose of doing memorization and also computation, right? And this also is a very, very interesting result from another Nobel Prize winner, and Leon Cooper actually wins the Nobel Prize for the discovery, joint discovery of superconductivity, and he formed a neuroscience research center. And at the end of the 1970s, he published a paper about this RC neural network. I believe at that time he just believed that this more or less looks like the functionality of a human brain, but not much people follow up because you need to include the fuzzy theory, control theory, and to better describe the nature of the neural network discovered by him. And actually our brain works according to this architecture. So you only have a 3-layer, and you see the 3 keywords are there, vector. So it's a feature vector, knowledge space, you see in the middle, knowledge space, and the time. Time means it's incremental learning and the training, right? Then how to store knowledge, how to memorize the knowledge, how to achieve incremental learning. It's like a human being. We spend 20 years in the school or 15 years in the school to get the university degree. Actually, this gives a full explanation already, all right? So you see knowledge space, feature vector, time. Done already, right? So I guess this is a very, very interesting discovery. But in the textbook, I guess not many people mention this one, all right? And the third know-how is about the cognition, because this is another weak pillar in AI, how to transform a sensory data or sensory signal into knowledge. Okay, that is a weak pillar in today's AI. And we are very strong to do the transformation of knowledge from one domain to another domain, or transform knowledge, okay, decision into motor signal so that let the robot to perform action. So these two phases are quite strong, but what is missing or weak phase is transformation from sensory signal to cognitive state of knowing the meaning behind the signal, right? But okay, this is the area that we have done some contribution. I believe for that weak phase, we more or less know all the steps involved inside already. Okay, so let give you a confidence about the current state of the art for us to venture into the invention of a humanoid robot, because we have more or less the 3 know-how, the know-how for the design of the body, the know-how for the design of the brain, the know-how for the design of the mind, etc. Right? So now I just quickly go through these 5 steps, which explain to you how to apply these 3 or the know-how in these 3 domains into the actual design of a humanoid robot. Okay, so maybe in this way it will help you to understand relationship among all the topics, okay, which will be involved in the design of a humanoid robot. And here I put the picture of Viggo Padovic, right? And he has actually discovered this criteria, ZMP, zero moment point. Okay, that is a very good indicator for us to measure stability for biped walking. Right. So now you see all the topic here, right? From design of appearance, design of a structure, mechanism, computing, memory, power supply, actuator, controller, etc. Right. So you can add in more. Okay. So these are the major topics in robotics. And all of them will contribute more or less toward the achievement of this 5 flow. Okay, so let's start from the flow of material, right? Okay, so then for the hardware, the material flow, actually material flow involved in the design of the body, but also in the design of the brain, because the brain depends on the material. So therefore, we want to know, okay, what is a body, all right? So body in robotics, we know that it's just a network of a link and the joint, right? And the inside the joint, we have an actuator, we have a sensor, right? Then how to control the actuator, we need to have a controller, all right? So this is quite straightforward. But then what is the material flow inside electronic brain, right? So if we just stop at the level of a neuron or transistor, it may not help us to have a better understanding about the electronic brain. This is why we need to go one level up, right? Think in terms of a logic gate. Then suddenly you see there's a common foundation between biological brain and the electronic brain, all right? So logic gate will create CPU, logic gate will create memory. So then you see it's magic, right? Okay, so then currently actually we have a know-how okay, about the material flow inside the body, the know-how about the material flow inside electronic brain. Okay, we have a full understanding already, all right? So there's no obstacle. Then in terms of mechanical body for appearance design, this is just an example of what we have done. And this is the prototype of the robot that we have developed with government funding. And then there are many other type of appearance design, mechanism design, and the structure design. Then in terms of mechanism, so this is our research work, but not much difference, okay, among all the humanoid robots. So you have a mechanism for arm, for hand, for upper body, for leg, etc. Right? And but only slight difference is about the modular design, because this is our attempt to come out the single module with a 2 DOF. By putting them together, then we can form arm, form the leg, etc. Okay, so we have do some research in this direction, and then other people's result for the achievement of mechanism design. Then you see Boston Dynamics robot, and also I guess this one should be the KAIST from South Korea, right? The HUBO, etc. Right? Then, okay, this is an interesting part. Okay, so in computer engineering, we already have a very good understanding about how to build the CPU, how to build the memory unit from the use of a logic gate device. All right, then inside the logic gate, we have a transistor, right? But our conclusion should be that the brain is a massive network of a logic gate. You should not say electronic brain is a massive network of a transistor, because that kind of statement does not help people to pay attention to the focus. All right, so this is quite standard blueprint for today's microcontroller, microprocessor, or digital computer, electronic computer, right? So we can leverage on the use of microcontroller, microprocessor to construct robot brain. But however, okay, you will see this is just a single unit of a microcontroller. But our brain, our conclusion is our brain is a massive network of this unit. If let's say we just name this entire slide as a brain cell, okay, use this one. If we consider this as a single brain cell, then we can say human brain is a massive network of such brain cell, right? Each brain cell is a microcontroller on its own. Right, that should be more accurate the description about the nature of a human brain and the nature of an electronic brain, and that gives us an indication about the development of a next generation of electronic brain, right, or fifth generation of the electronic brain. Okay, so that is the value of the last slide. Then we can leverage on this result to come out the solution for electronic brain for our robot. Okay. So by now it's clear, okay? So there's no obstacle for us to understand the material flow inside robot's body, no obstacle for us to understand the material flow inside robot's brain. However, the understanding of this common ground at the logic gate level actually, I guess will encourage more people to venture into the direction of developing brand-like computer, right? Then for energy flow, I guess not much obstacle there, okay? Because it's like a human being, we have a lot of muscle. Then inside the robot, we have a lot of actuator, and we have a servo motor, like etc., right? And then we have a lot of control loop. Then we need to supply the power, etc. Okay, and one way to understand this energy flow is from this viewpoint of IoT, like Internet of Things. Actually, a robot is a mini version of IoT because a robot is an Internet of a sensor, Internet of actuator, Internet of microcontroller, etc. Right? So then we need to have distributed the power supply, okay, to all these energy consuming device, etc. Right? And so I guess let's say for the controller dedicated to the motor, or the controller dedicated to the high level reasoning or cognition, recognition, etc. So we need the power supply. So therefore, the solution should be distributed power supply. Okay, and the only thing is how to make the power supply, okay, last for longer hours, such as 4 hours, 8 hours. I guess we are among the first one to make use of a fuel cell. All right, so with the government support, 12 years ago, we have the fuel cell power supply system. It could last for 4 hours, 8 hours, okay? So it is better than battery, all right? So it is the only development we need to further, okay, advance to lower down the cost, because the fuel cell power supply system is quite expensive. The battery is cheaper, right? And another innovation could be how to convert electric power into mechanical power. And the conventional solution is to do one-to-one conversion. And at each joint, we have a motor, right? Then a motor is a mechanical power supply, okay? You take electric power as an input, mechanical power as an output, right? And if one motor fails, the entire arm will fail, etc. But here we have developed a solution with a single motor, right? It can distribute output or have a network of distributed mechanical power, right? So single motor, and that motor can power multiple joint. If we do such a system in parallel, let's say 3 motor to support this network of distribution of mechanical power, then only when all the 3 motors fail, then this robot will fail. As long as one motor is working, this entire robot will work. All right. So this is the work done by us. And here you see the prototype for robotic arm. We have a single motor to power 20 degrees of freedom. And for this 3-fingered hand, single motor to power 9 independent degree of freedom. And for this dual arm, each arm has a single motor, then 6 independent degree of freedom. All right. So this could be interesting. Okay. So, okay, I just move on. Then, okay, so other result for the transformation from electric power to mechanic power. I can skip all this video, right? So this is an example done by others, right? So in terms of energy flow, so just remember inside we have maybe electric energy or chemical energy. If you use a fuel cell, the input is a chemical energy, then we must convert it into mechanical energy, right? So only concern is do we have a one-to-many conversion or not with a single motor, then to build up a network of distributed mechanical power, etc. Now the more complicated part should be signal flow, right? So it's like a human being. We are living inside an ocean of a signal, right? So actually, we are like a fish, we are surrounded by all kinds of signal. And then we have a very, very powerful sensory system, okay, to transform all the sensory signal into cognitive state or knowing the meaning behind the signal. Then could we make today's robot have the same feeling? So they are living inside an ocean of a signal. Then they will feel comfortable, okay, to handle all kinds of inflow of sensory signal, right? And also besides a sensory signal, we also need to have a control signal, right, to control our muscle control actuator. So this will be very complicated flow or layer for the design of a robot or for the design of a humanoid robot, right? So here just a simple example for the, let's say, position control with velocity in the loop, etc. Okay, so good news to us is with advance in control theory, so we know how to handle, okay, the feedback control, okay, as long as we know what should be the desired position, desired velocity, then to output desired motion should be not an issue, all right? Then for the grasping, again, we also need to have a signal, okay, about the pressure, tactile sensor, etc. Right? So then once we know this signal, then it's not the issue for us to close the loop, okay, to achieve desired motion, and also the force torque sensor, etc. Okay, for us to achieve human robot interaction, which make use of force signal, torque signal, etc. Right? So and also visual signal, right? So today we have a camera to capture inflow of a visual signal and try to understand the meaning inside. So it's not the, but it's still a big issue, right? This is, I guess, one of the most challenging one, okay? Because for us, we have a capability to understand photo, understand image. But I will talk about this when we reach the knowledge flow, okay? So this could be a challenging part, okay? Then for voice, all right? This also could be a challenging part, okay? But just as a simple voice, treat the voice as a signal should be easier, right? That means interact with robot with the use of acoustic signal should be easier. But how to interact with the robot with the meaning behind the acoustic signal, that should be a challenge, right? Okay. And you will see today a lot of research group try to combine vision and speech together. Actually, both of them, the output could be more or less the same. So it's knowledge-based output, right? And something special to robot should be the motion, right? So without the motion, then the robot should be useless, all right? So the two, I guess, the two key word behind robotics should be motion and intelligence, right? And today we are more or less very comfortable with achievement for motion-related result. However, okay, now we need to put in more effort to achieve intelligence-related result. Okay, but motion flow is also quite complicated because we can talk about the motion which are related to locomotion, motion related to manipulation, motion related to the grasping, and if the robot can fly, can swim, can dive inside the water, then you see it's quite complicated. And in particular to this conference team, the one keyword is walking, another keyword is climbing. Walking, the biggest challenge for walking should be stability in walking, and the stability actually talk about the stability of a motion controller, okay, for walking or climbing, right? So this should be one key focus for the team of this conference, right? And then for the motion, okay, related topics, then here just now I already mentioned, okay, locomotion depends on motion, manipulation depends on motion, grasping depends on the motion, all right? And this slide basically showing you the inner loop and the outer loop, which eventually will involve in the motion control, but at least signal-based motion control and actually just an inner loop, okay? If we want to achieve intelligent control of the motion, then you see the outer loop will play a very important role, okay, etc. If now, let's say we look at the grasping, then we can identify these action. So we can always relate motion to action, action to task, task to the job, to the mission. So you see there's a pipeline, okay, of a flow from knowledge to the motion signal, control signal. You see knowledge all the way to the motor signal. Actually, in this flow, from knowledge to motor signal, there is a description of a task, description of action, description of the motion, then equation of the motion, all right? So this just showing you the motion flow at the second part in this in this pipeline, right? So, and now you see the relationship between action and the motion. For action, grasping related action, we can open the hand, close the hand, then move the hand, then stop, okay? Pull in, etc. Then once we know the action, then for each action, we need to identify the motion description and in particular, the motion equation, right? And here you see, I show you the motion description in task space. Once we know inverse kinematics, inverse dynamics, then we can move this motion equation from task space to the joint space, etc. Then for manipulation, it's the same. Okay, try to relate motion description with action at the higher level. Then above action, there's a task. Okay, then on top of task, eventually is a job or mission, etc. So this is a pipeline of a flow from knowledge to motion. Okay, then just at the action level, you will see the manipulation involve a push, pull, grasping, throw, follow, etc. All right. Then once you go to the lowest level, more or less the same because we can always assign a coordinate system to two tip or fingertip. So therefore, at the lowest level, the motion equation should be the time function about the XYZ coordinate, then time function about the angular position theta, something like that. And eventually interaction force, which involve 3 force components, 3 torque components, etc. Right? And the complicated part should be the biped walking. Then you see we have 2 legs, and each leg can undertake some action, right? And by combining these 2 legs in a different way, then we have a rich set of gait, right? Pacing gait, walking gait, trotting gait, and cantering, galloping gait, etc. Right? So it's quite interesting. And eventually, humanoid robot can undertake crawling kinds of locomotion, etc. So this should be a very, very complicated description for the motion flow, etc. Then once we have a motion equation in task space, I guess it should be quite straightforward for us to transform motion equation from a task space into the joint space. Once we reach the joint space, then we can directly connect it with the motion control or feedback control system. Okay. Then once we activate the feedback control system, then the output from the feedback control system will be the performed motion from a robot's body, right? So this should be quite clear. But the complexity is how are you going to combine all this together? You see, upper body can undertake manipulation and the grasping, a lower body can undertake biped walking, and then at the higher level we have action. Then above action we have a task. Then on top of a task we may have a job, etc. And then we may also have an intention because there's a brain layer, there's a mind layer. Robot has his own intention, and maybe the sensor may tell the robot something urgent happens, etc. You see, so that creates a little bit of complexity. But despite such a complexity, then with heavy investment by in the private sector or by government, then you see today we are able to achieve more or less a human-like motion. So I'm not going to play all this. Okay, so it's not the issue at all, right? And then what should be the motion equation? I guess I can quickly go through it because in robotics, how to describe motion equation, which let's say relate the interaction force with additional torque at each joint. So we can apply static equation. Then for dynamic equation, if we have extra energy to use in order to produce a kinetic energy, then you see acceleration by the robotic arm. So we know all this equation. One thing special is about the kinematic equation because humanoid robot has a network of a link or joint, all right? And each link could serve as a base link. It's not like an industrial robot. The base link is always fixed, okay? But for humanoid robot, the base link could change, all right? So therefore, we need to have this matrix of kinematic equation, right? Then for each element inside the matrix, okay, we know the equation. Okay, so it's not the big deal. But the challenge, it could be the dynamics description and the control, right, for biped walking. So because due to the gravitational force, right, so this will make the biped walking to become unstable. So this in this area, we still have a lot of theoretical study. Okay, for example, we have inverted pendulum model to describe describe the dynamic equation of biped walking. So I'm not going to enter into the detail of description of all these equation. So actually, okay, so we have a know-how, okay, how to describe the dynamics relationship between the force torque and the acceleration force and the motion, okay. And this is a method proposed by Japanese researcher, cut table model, right? So it just model lower body as a table, upper body as a car, which move on top surface of the model. Then between upper body, lower body, there's a dynamic interaction, okay. Now here you see the ZMP, zero moment point. But this is a very good indicator for us to monitor the stability and eventually make use of a ZMP to guide the planning. What is the next footstep? Okay, so in order to achieve a new stability, etc. Right? So then we have all the detailed equation. Okay, so it's not the issue. Okay, and actually we can also make use of a result from industrial robot. We can treat the leg as an inverted arm. Okay, then we can use a result of a static equation, dynamic equation of a robotic arm to understand, okay, the dynamic property of biped walking, etc. Right? So this is not the issue. And then, okay, I believe every one of you see this, okay. So just give you a quick impression about today's achievement, okay, for robot to perform a human-like skill, right? So not much difference, right? Okay. So I guess I still have 10 minutes. Okay, the last topics will be more challenging. Okay, so okay, I almost reached the last layer. Okay, in today's talk. So let give you a very convincing result about today's achievement for human-like skill. But the biggest remaining challenge should be this layer: how to achieve human-like intelligence. All right, and today there still has a lot of discrepancy about the philosophy. And the biggest discrepancy is about the nature of a human being, because still a lot of people believe that the human being is just an embodiment of the body and the brain. Mind is part of the brain. Actually, that does not help us to make a progress. And the evidence is what AI has been in place for 70 years, 7 decades, all right? So not much breakthrough, right? So this is why we need to move away and continue to adopt this more accurate okay, understanding about the nature of the human being. Just is an embodiment of a body, brain, and the mind is mind, brain is brain, etc. Right? So in that sense, then you will understand, okay, what is a knowledge flow, and what is a weak point or weak phase for us to achieve this complete pipeline of a knowledge flow, right? So that is very important. And then you will see the keyword cognition. But actually, not many people pay attention to cognition. If you look at the name of the lab, a lot of labs use the name pattern recognition, right? So recognition is a very popular term, but actually cognition is very important. So without achieving cognition, how could you do recognition, right? So this is a big issue, okay? So at the philosophical level, we must clear this discrepancy about the philosophy behind the development of robot man, all right? Okay, and the goal is to achieve human-robot interaction at the cognitive level. Today, a lot of research occur at the human-robot interaction at the signal level. You can pick up a human brain signal and use the matrix to map into motor signal, then do some demonstration. I guess signal to signal transformation is not the big deal, because in mathematics, this is a trivial. Signal to signal transformation, I believe, is not the big deal, right? The big deal should be signal to knowledge, knowledge to knowledge, and then knowledge back to signal. That is a challenging part, right? So this is our research work. Okay, you see more than 15 years ago, we already have this idea of developing a robot twin, all right? So we program a robot twin, a digital robot, interact with the digital robot. Once everything okay, then let the digital robot to control the physical robot. And today, this become a popular term, digital twin, etc. And now we talk about the MEDA. Basically, it's a virtual space or virtual human being, all right? So the challenges, I guess, remaining challenge is this one, right? And also, Singapore government has funded us a project to do research in this area, right? So in particular, because for us, we can use a human language, okay, natural language to interact among ourselves, right? Then in future, this is a scenario we would like to achieve, okay? Let robot to master human language, right? So therefore, robot could interact with all kinds of people, right? Today, if you want to instruct a robot to do something, then you need to know how to program a robot, right? If a robot can master human language, then everyone can interact with the robot. And this is a research result done by us with the funding from the Singapore government. So it is to develop a human-robot interaction with the use of human language, right? So not at the signal level. So I skip this one. And here is a typical example, okay? Human-robot interaction at a little bit cognitive level, just focus on the hand, which is closer to the eye, just a little bit the meaning there, right? And but this one actually show you this pipeline, okay, of transformation from visual signal to knowledge, knowledge to knowledge, and then knowledge back to motor signal, right? So this help you to understand we must focus on this pipeline of a flow, which include signal flow, motion flow, and the knowledge flow, etc. Right? And then besides transformation of a sensory signal into cognitive state of knowing the meaning behind the signal, another important aspect about the knowledge flow is the biped walking. And because stability is a major concern on Earth, we need to overcome the gravitational force, okay, acting on this sagittal plane and this coronal plane, all right? So in these two planes, vertical plane, okay, stability is an issue, right? And I guess there is some discussion about what do we mean by stability? Is there any definition about stability? And here I just help a little bit to understand. Actually, we have two types of stability. One is the stability of dynamic walking, stability of static walking. All right. For dynamic walking, then acceleration. If there's acceleration play an important role, then we talk about the stability of the dynamic walking. All right. If acceleration does not play a major role, then it is a stability of a static walking or something like that. All right. So still, again, there's some discussion there. And it is also very interesting for us to focus to try to understand the animal with 4 legs. All right. Because 4 legs actually divided into 2 biped. So we can consider 4-legged animal actually make use of a pair of a biped walking system. All right. So then in this way, they coordinate this pair of a biped walking system in order to achieve stability. So it is quite interesting. And also it's very important for us to understand the action, because on top of a motion, there's an action. Then we need to know what is the action delivered by each leg. So here you see, these are the 4 major actions delivered by each leg: support, carry, push, swing. Then we combine, since we have a 2 leg, then we can have different kinds of combination. This may help us to better understand the biped walking mechanism, instead of just talking about the single leg support, double leg support, right? With this combination of action, then we have a better understanding, okay? And today, to achieve stability, the knowledge about the biped walking and more or less is there, right? Okay. Then, okay, this just showing you, we have done some exhibition about our robot. It attract a lot of public interest. And also we reduce the size of our robot, okay, to the handphone size robot. Then in this way, we may have a robot tutor for students, right? And okay, so more or less I achieve this goal within 1 hour to finish this lecture. So now to just a quick conclusion, what will be the future challenge for us to pursue, all right? So I guess the future challenge is to achieve robot self-intelligence, all right? And then this is slide, basically it gives you the confidence about this possibility. We have one, two word. The two here basically, okay, this is another, I believe this is another mental obstacle which prevent the breakthrough in AI research. Because you look at the terminology, we always consider language is the application domain of AI. Actually, that is a misconception. Language should be the tool which will enable human being to grow the intelligence, which also enable machine to grow the intelligence. Another aspect is a tool war. I guess this is also more or less more people start to agree. We have a physical war. We also have a conceptual war or mental war, right? So we must make a disconnection between these two, right? Then we have three type of intelligence. We have a human intelligence. We have a computer-aided human intelligence. Then we have a machine self-intelligence. Then we have a four pillar, right? How to represent knowledge, how to acquire the knowledge, and then how to compute the knowledge, how to apply the knowledge, etc. But always remember this loop transformation from signal to knowledge, knowledge to knowledge, and knowledge back to signal, right? And then with our work, I believe you see the history of AI is upside down now, okay? First generation, aim at a very high level. Second generation, talk about development and the learning. Actually, I believe a true foundation of AI should be language and cognition, all right? And when we study, okay, robot intelligence, machine intelligence, it's always good to do comparison between human intelligence and the robot intelligence. When we do the research about machine learning, it is always good to compare human learning and robot learning, etc. Right? And we should never forget about this prerequisite for any machine to undertake self-learning. So we must make robot to be educable first, all right? Okay, thank you for your attention, all right? So within 1 hour, more or less, I complete my...
Thank you very much, Professor Ming, for showing just how rapidly in the last few years the gate of humanoids has improved, GAIT, with motion more fluid than most human beings can achieve.
Yeah.
That's incredible. But before I open for the questions, I can't resist picking on an interesting point you mentioned, Nikola Tesla's statement many, many years ago in history about if we want to understand the universe, think energy and vibration. And what was the third?
Frequency.
Energy, vibration, frequency.
Yeah.
I'm sure you realize that's exactly how many modern physicists think who propose string theory rather than point particles. The energy and vibration belongs to strings, not to point particles. Anyway, having said that, I'm sure you, So I invite questions, please. The Chair, how long can you allow for questions as we're running a little bit over time? Yes, fine. Yeah, okay. So please.
How far do you think we are from having the robot that can talk and with us and do the things, understand and do the things that we say?
Okay, so that depends on the deployment of the resources, because today you see in the research community, so a lot of competition for resources, right? And then you will see people get a lot of resources. Actually, they do not move in the right direction, right? So for the human-robot interaction at the cognitive level, just now you mentioned with the use of human language. And more or less, I don't see any obstacle anymore at this time, right? So you look at because I did not mention the achievement by industry in speech recognition. So what is lacking is speech understanding. So, but Singapore government gave us a project 12 years ago, just focus on this this gap, to bridge the gap, okay, or extend speech recognition to speech understanding. So we more or less the knowledge funding are there. But since this is something I do not like, because you remember the most valuable, I do not know if we have a policy maker here, look at the nature of research, because we have a lot of research, they just create results from no solution. Then they absorb a lot of resources. If we pump in the financial support resources into the right direction, I guess maybe a few years time, it's already there. Okay, and you see a lot of companies, they try to make a false claim, they are already achieved that. Actually, it's not, there are human beings behind, right? But in terms of methodology, I do not see obstacle, because first thing we need to do is to have a smart e-dictionary. Today we do not have, okay, or smart dictionary, okay? Then I did not present our work about the no-nel or something like that, okay? So we need to have an e-dictionary or smart dictionary, right? So that bridge the link, that means combine audio signal together with the visual signal. Because when we refer an object, you see the appearance or something like that. So we need to do that, but that is missing. Actually, we are able to do it, but no company finance it, no government pumping money to do it. But a lot of money has been spent on deep learning, on other things which I believe is in wrong direction.
Yes, yeah. Sorry, switchboard. Yeah.
Thank you. So you mentioned that human-like robots are the best to teach STEM at schools. So the practice until now shows that most robots used at school are using wheels, probably because it's an easier to implement locomotion system. But how do you see the future of robotics in schools?
Okay, so I believe in Singapore, because Singapore is very special, we have a 4 national language. Chinese, English is a working language. We have a 4 national language, 1 working language, all right? So then we discover the biggest challenge to educate our young kids is language, to teach language and the mathematics, right? Then with our framework, actually we consider mathematics is part of human language. So human language include natural language, programming language, and the technical language. Technical language is mathematics, all right? So just now you mentioned, okay, how to do the hand-on, to do, okay, put together, okay, or Indian language, whatever. So that is, I guess that should be the focus for robot tutor. Because when students are very good in, let's say, natural language, programming language, and the technical language, I guess he's ready to study any subject, I believe. So that should be the focus. Robot tutor to help our pupil, kid, to master human language, which include natural language, programming language, technical language, right? But to play, you see, you have Lego. That one, it's okay. Like we have all kinds of robot construction kit. I believe language, human-robot interaction, cognitive level, right? That's very important. Yeah.
Thank you very much.
Okay.
Okay, then I think we adjourn for coffee break. But once again, the hand for you've given a tremendous perspective,
Yes,
so broad and sweeping. Yes.
Yeah. Okay, thank you. Yes, thank you for your attention.